Alright guys, today we're going to talk about slope fields, which are a somewhat tedious item that we have in our curriculum. There's not a ton that we really use slope fields for, but it could appear on the AP exam, so we have to make sure that we've gone over it. I will say that for the most part, they're pretty easy and straightforward. What you are basically doing with a slope field is you are finding the slope at different points and you are drawing a small tiny linear segment that represents the slope at that point. Okay, so for this first example that I have here for you, our differential dy dx is y. And let's say that our x's go down the left-hand column and our y's go along the top row. If we try to find the value of the derivative at each of these points, they're going to be completely dependent upon the y value. So if y is -3, as it is in that first column, then the slopes at each of these points, because the y is -3, are all going to be -3. The slopes at any point where y is -2 are all going to be -2. Well, maybe I want my negative. There we go. The slopes anywhere where y is -1 are all going to be -1. Slopes anywhere where y is 0 are all going to be 0, no matter the x. Okay, so obviously this is always dependent upon, this one in particular is always dependent upon the y value. That's not true for every differential, but it is for this one. Now, once you get these values, these are your slopes at your different points that are on this coordinate plane given. We want to draw, like I said, tiny little segments that represent the slope at each point. Now, just so we're clear to begin with, you do not have to have your slopes be absolutely 100% perfect. No one is going to be checking, is the slope where it's supposed to be 1 going to be exactly 1? What they want to see is that your slopes get steeper when they are bigger slopes, or shallower when they're smaller slopes. And they are in the correct direction. So obviously a slope of 3 should be steeper than a slope of 2. A slope of 2 should be steeper than a slope of 1, and so forth. And then if you ever have 0 or undefined slopes, those should be either horizontal if they're 0 or vertical if they are undefined, so that you have the correct value there. Okay. I'm going to go ahead and show you a picture. I have a picture of mine somewhere. Maybe not. I thought I had a picture. Aha. So let's get rid of all my little dots here. When I clicked it, it's supposed to come up, but it didn't before. Okay, so here is a picture of my slope field for this one that I had taken off of my notes and just put up here to come up easy, so that you could see this all drawn out. Okay, again, they're not perfect, but they have that general slope that they're supposed to have. The way we may see these on the AP exam, anytime you're going to draw one, obviously it has to be a free response. So if you're drawing a slope field, it's got to be a free response question. Usually it's one part. They'll give you a coordinate plane and ask you to draw the slopes at the given points. Usually I would say they're anywhere from like 12 to 15 points. Maybe 20 is the most that I've seen. But no more than that. Okay, so these are a little bit more than you're probably going to see. But the most difficult part is that these are kind of tedious, and depending on how difficult the differential is, your slopes could be different. So I do want to take a look at one where they're dependent upon both x and y. This one was only dependent upon the y value. Let's take a look at another one where we're dependent on both our values. Okay, so this one is called negative x over y. Okay, this differential is negative x over y. This is one where we're dependent upon both of our variables. So I'm going to go ahead and fill in this chart here for our different slope values. Again, x's are going down left-hand side column, y's are across the top. So for this first one, our slope would be +1. And let's go across the row. I'm going to do decimals because I just think it's easier for you to judge when something should be steeper if you have decimals rather than fractions. So this would be 3/2 or 1.5. Next would be 3. And then when y is 0, notice y is on the bottom. So when y is 0, these are all going to be undefined. So I'm actually going to, let's see what I can fit. I guess I could fit U and D in here. And I'm going to go ahead and fill those in for all of these where y is 0. Because all of those are going to be undefined since y equals 0 would be 0 on the bottom. Okay, and then I'm going to keep going on the other side. Once I plug in. All right. So a pattern does start to emerge. We see that we have the negative of what we had on the other side. Okay, so it's a little bit symmetric. Let's try the next row where x is 2, and we have these different y values across the top. So first we would have 2/3, which would be 0.67 as a decimal. Okay, then we would have 1 and 2. Then on the right-hand side, after that undefined, we'd have -2, -1, -0.67. When x is 1, we're working through here, we'd have 1/3, which would be 0.33. Let's clean that up. Okay, so that would be 0.33. Then we would have 0.5, 1/2, and then we would have 1. And then we have the opposite signs on the other side. They are symmetric. All right. When x is 0, all of these are going to be 0 except when y is 0 because 0 over 0 is undefined, but the others are going to be 0. When x is -1, we have -1/3, so -0.33, -0.5, -1, and then the opposite signs. So we have quite a bit of symmetry going on here. Then when x is -2, we have -2/3, so -0.67, -1, -2. On the other side, we have the positives. Okay, when x is -3, we have -1, -1.5, -3, and then the opposite signs. Now, we have quite a few that we have to draw here, quite a few different slopes that we need to draw. The hardest part for one like this is that we end up with a lot of different slopes, and so we have to keep track of a lot of different things. For example, think about all of our positive slopes. We have 1/3, 2/3, 1/2, 1, 2, 3/2, and 3. Okay, so we've got a lot of different positive slopes, and we need to make sure that we are going up in our steepness. Okay, so obviously 2 needs to be steeper than 1, 3 needs to be steeper than 2, and so forth. So it's a lot to keep track of. Sometimes it might be easier to just do the same slopes at the same time. So anywhere you have a slope of 1, do those kind of first, and that's kind of your basis for moving off everything else. That might be a little bit helpful. And then you have to fill in the rest of yours. Obviously, make sure your 0 slopes are horizontal, your undefined slopes are vertical, and we should end up with somewhere. I do have a graph. There we go. There's mine. I'm actually going to move it a little bit. Okay, so there is our slope field for this one. Notice that we do have those 0 horizontal slopes when x is 0 except at the origin. And then when y is 0, we have vertical slopes. The rest of them slope together depending upon how steep they are. Also notice that this is a little bit, this kind of looks almost circular. If you get -x over y as your dy dx, then that is a circular function to begin with. So that means that our slopes kind of mirror what the slopes of the actual function are. That's what the slope field is supposed to represent, the slopes of the possible solutions. So what we're seeing here, our slopes should kind of mirror what an original function would look like. And so if this original function was circular, then the slopes should kind of be circular when we look at them. Okay. Let's also take a look at some matching. Okay. We have 4 slope fields and we want to match them up with their differentials. Couple of things that I would go through when I'm looking for these. Right away, I'm drawn to number 6, which is in terms of x only. Okay, so all of your, for example, x equals 0 should have a slope of 0. When it's x equals 1, should be a slope of 1. When it's x equals 2, should be a slope of 2. So when I start to look at which graph kind of fits that bill, we could see that B matches up. Okay, with that description. And again, you can plug in some values. Like I said, when x is 0, slopes are 0. When x is 1, slope is 1. And it should get steeper as we go to the right. And should be negative slopes when we are to the left of 0. And it should be getting a steeper negative slope as we get more to the left. Number 5 is solely dependent. I'm going to mark out B. Number 5 is solely dependent upon y. The last one was only dependent upon x. So this one is only dependent upon y. And we could pick out some easy ones. If y was 2, our slope should be 0. If y was 1, our slope would be 1. If y was 3, our slope is going to be negative 1. If we start to take a look at these graphs, that fits with A. All right, let's take a look. Number 3 is solely dependent upon x again. It's sine of x. So we could plug in some quick values. When x is 0, the slope should be 0. When x is, say, between 0 and pi, then that's still going to be a positive slope. Once we pass through pi, it's going to become a negative slope. So also think about sine function is a derivative of a cosine function. And so our slopes should be periodic because our functions are periodic. And that seems to match up with C. You can plug in some values and make sure, like we talked about, make sure it matches up, but that matches up with C. And then by process of elimination, then 4 has to match up with D. But let's talk about a couple of things. This one's dependent upon both the variables. So it's not going to be all the same for an X or all the same for a Y. But we could easily figure out where would these be 0. They'd be 0 when they're equal to each other, right? When X and Y have the same value, they'd be equal. So that's kind of along the Y equals X line. And if you notice, along the Y equals X line, we have slopes of 0 when these are equal to each other. So that matches up. All right, let's try another set of 4. We're going to match up to these differentials. I would again kind of take a look. Do you have any that are dependent upon one variable only? Number 7 is dependent upon x only. So when x is 0, your slope is negative 1. When x is 2, your slope is 0. So if we start to take a look where x's are all the same slopes, and a slope of 0 when x is 2, that kind of matches up with B. Okay. Number 8 is solely dependent upon the y value. So whenever y is 0, for example, your slope should be 0. As we go up above 0, the slope should be getting more steep in the positive direction. When we go below 0, the slope should be getting more steep in the negative direction. So that matches up with C. Number 9, we actually already did. That was our second example where we drew the slope field. That was negative x over y. Remember, that was circular, so that actually matches up with D. And then number 10, x plus y, that's dependent upon both of your values, and both your x and y, but notice that we could easily see when these are the opposite signs of each other, so like along the y equals negative x line, we should have 0 slopes. Notice that that happens along the y equals negative x line. This one matches up with A. It's kind of the opposite of the one we had before. Okay, here are 2 examples of something you might see on the AP exam. They give you a slope field and they ask you which differential this matches up with. Okay, so I would immediately start to take a look at your slope field. What are some characteristics that you can figure out? And I would notice that for this one, number 11, so let's take a look at that one first. For number 11, These all seem to be dependent upon the y value. Notice that at each y value, the slopes are the same amount all across horizontally at the y value. Okay, so they're all the same amount as we go through those y values. We are a zero slope at y equals 0. So that could be useful. Notice that A and C are not only in terms of X, so we can get rid of those, or excuse me, not only in terms of Y, so we could get rid of those. B and D are in terms of Y. Now we said at 0, the slopes are 0. That could not work for answer choice B because when Y is 0, these slopes would be undefined for answer choice B. So we have to use answer choice D. We might also have noticed that the slopes are always either 0 or positive. So y squared makes sense because that would always be either 0 or positive. Let's take a look at number 12. So for this one, all of them are in terms of both x and y. Okay, and notice that that matches up with the graph. There's nothing where all the same x value has the same slope or all the same y values have the same slope. So I would start to notice anytime my eyes are drawn to 0 slopes. And when I do take a look at this, I notice that I've got some 0 slopes along this y equals x line. And so what that's telling me is that when y is equal to x, my slope is 0. So if I go take a look at these differentials, my thought is to look for which one is going to have a 0 slope when y is equal to x. The only one that's going to work for is B. Okay, so answer choice B, the slope would be the same. So that definitely matches up with answer choice B. All right, so one more, same deal. We just have 5 answer choices instead of 4. We want to match this up with the differential that it would go with. The first thing I could tell right away, I'm definitely not going to use B because B is only dependent upon X, and we can see that we don't have the exact same slopes when we have a specific X value, so we know that doesn't match up. Something that might make it easier to figure out which one works is we could actually rewrite these. Think about answer choice A. We could take out a y, and that would be y times x plus 1. For D, we could take out a y, and that would be y times x minus 1. For E, we could take out an x, and that would leave y plus 1 inside. And so now it becomes a little bit easier to see where these things should be equal to 0. For answer choice A, we should have y equals 0 have a slope of 0 and x equals -1 have a slope of 0. And we notice that that does not happen in the graph. For C, when they are both equal to 0, we should have a slope of 0, and that's not happening. It looks like that when the x is 0, we might have a slope of 0, but not for the y equals 0 along the x-axis. So already we've canceled out A and C as possible answer choices. For D, we should have slopes of 0 when y is 0 and x is positive 1. I'm not seeing that, so it's got to be E. Let's see if that checks out. When x is 0 and y is -1, the slope should be 0. And I already said it looks like it when x is 0. And also, if you take a look, when y is -1, our slopes are 0 there as well. So this one matches up with E. Okay. So taking a look at some of those characteristics of the slope field, especially where you may have 0 or undefined slopes, can really help eliminate answer choices or find the correct answer choice. So always keep that in mind when you're matching up slope fields to the differentials. That can help a lot. That can also help you when you are trying to pick a slope field. The other way that we might see these questions, like I said, it might be the reverse of what we just did with the last 3. The last 3, they gave us a slope field and they asked us to pick the differential. They could give us the differential equation and ask us to pick a slope field. So our slope field could be our answer choices that we have to choose from. But we would still be using the same kind of skills. Where is it equal to 0? What else matches up? We can plug in some more points if we needed to in order to eliminate some answer choices.